Welcome to this explainer. Today we're taking a completely fascinating macro to micro journey through the IGCSE topic of the states of matter. Whether you're prepping for your exams or you just kind of want to grasp the invisible architecture of our physical world, well, you're in exactly the right place. We're going to observe exactly how particles behave, shift, and interact, focusing entirely on the raw chemical mechanics to give you a pure, structured understanding. To kick things off, I want you to think about this everyday question. We see ice melting in our drinks, water bubbling away on the stove, and steam seemingly vanishing into thin air literally all the time. But what's actually happening beneath the surface at a microscopic level? Today, we're diving into this everyday phenomena by looking at the invisible chemical mechanics driving these transformations. We're going to unearth the hidden rules that dictate exactly how everything around us holds its shape, or well, loses it.
Okay, so here is our roadmap for today. We'll cover the three core states, compare their properties, map out the 6 state changes, decode heating curves and energy, zoom in on Brownian motion and diffusion, and finally, lock in those essential exam phrases. This will arm you with the exact knowledge and structure you need to absolutely ace your exam.
Section 1. The 3 core states. Let's start with our baseline. We're going to visualize the macroscopic physical states we interact with every day by zooming straight into their microscopic particle models. I want you to imagine these particles dynamically. In a solid, they aren't just sitting there. They're locked firmly in a rigid grid, vibrating slightly but held strongly in place by powerful forces. Now, when we shift to a liquid, the rules completely change. The particles are still close together, but that rigid structure is broken, allowing them to freely slide past one another. This is exactly why liquids can pour and take the shape of their container. And then we have gases. Here, the particles have broken free almost entirely, widely spaced and chaotically bouncing off the walls of whatever container you put them in. In fact, a gas is mostly just empty space, which is why they're so easily compressible, unlike solids and liquids. Understanding these 3 distinct behaviors is the absolute foundation for everything else we're about to cover. Section 2. Comparing state properties. Let's see how these models build into the exact analytical framework that examiners highly reward. Memorizing this specific comparison table layout is essentially your golden ticket for securing marks on particle properties. Examiners absolutely love this structure. For solids, the arrangement is regular and closely packed, the movement is purely vibrating in fixed positions, and the energy is very low. Now, for liquids, the arrangement is random but still close, the movement involves moving around and sliding, and the energy is a bit higher. Finally, for gases, the arrangement is completely random and far apart, the movement is fast in all directions, and they possess the highest energy. If you can recreate this grid in your mind during a test, you've got a foolproof system for comparing any state of matter. Section 3. The 6 state changes. Now we need to understand the transitions. What exactly happens when matter shifts from one state to another? These are the 6 directional state changes you absolutely must master. We all know melting, from solid to liquid, and freezing, which is the reverse. We're familiar with boiling, liquid to gas, and condensing, gas back to liquid. But I want you to specifically pay attention to the extreme jumps shown here at steps 5 and 6, sublimation and deposition. Sublimation is when a solid completely bypasses the liquid phase and turns straight into a gas. Just think of dry ice producing that spooky fog. Deposition is the exact opposite, where a gas drops straight into a solid state, kind of like frost forming instantly on a freezing window on a harsh winter morning. Knowing all 6 by name and understanding their directional flow is totally non-negotiable for a complete understanding of this topic. Section 4. Heating curves and energy. Now we add heat to the system to analyze real-time graphs and see energy actively breaking particle bonds. So, the crucial point here is understanding latent heat. If you look at a heating curve graph, you'll see the temperature rising steadily, but suddenly, right at the melting point or boiling point, the line completely flatlines. Why does it do that? Well, even though you're constantly adding energy by heating it, the temperature stops going up. And this is because that added energy is no longer being used to raise the temperature, it's being entirely consumed to break the intermolecular bonds holding those particles together. It's hidden energy, or latent heat, doing the heavy lifting of forcing a phase change. And this brilliantly illustrates the math behind it all. When that heating curve flatlines, we can calculate exactly how much energy is being used. Energy, represented by Q in joules, equals the mass of the substance, m in kilograms, multiplied by its specific latent heat, L. So Q equals mL. This simple but incredibly powerful equation lets you quantify the invisible effort required to tear those particles away from each other. Definitely keep this equation in your back pocket. It perfectly bridges the gap between conceptual physics and practical IGCE calculations. Section 5. Brownian motion and diffusion. Let's zoom in even deeper into the invisible chaos of particle movement to look at two highly specific scientific phenomena. It is incredibly easy to mix these two concepts up, so let's make sure we clearly separate them. Brownian motion describes the completely random, unpredictable bouncing of individual microscopic particles when they collide with smaller, fast-moving molecules of a fluid or gas. It's pure, localized chaos. Think of dust motes dancing erratically in a beam of sunlight. Diffusion, on the other hand, well, that's the big picture. It's the overall net movement of particles spreading out from an area where there are a lot of them, a high concentration, to an area where there are fewer, a low concentration. Think of a single drop of dark ink hitting a beaker of clear water. The erratic jigging of the individual ink particles, that's driven by Brownian motion. But the way that ink gradually and beautifully disperses until the entire beaker is evenly colored, that overall spreading process is diffusion. Section 6. Essential exam phrases. Let's wrap up the teaching segment by loading up your arsenal with the precise terminology required for success. Now, if I can just lean in and share an examiner's secret with you for a second, knowing the concepts is really only half the battle. Knowing the exact phrases the mark scheme demands is the other half. When you're asked to describe the movement of particles in a liquid, please do not just say they move around. You must always use the phrase slide past one another. And when describing a gas, random chaotic movement is your magic phrase. Using this specific, precise terminology is exactly how you guarantee full marks and show the examiner you truly speak the language of science. To quickly recap this explainer, you now have a highly focused roadmap. By mastering these microscopic models, retaining the exact layout of the properties table, applying the Q equals MCL equation to understand the flat lines and heating curves, and memorizing those specific mark scheme phrases, you have built a complete, highly practical toolkit for the exam. You haven't just memorized facts here, you've actually learned the structured mechanics of matter itself. As we finish up, I want to leave you with this somewhat provocative thought. Throughout this explainer, we've seen that adding energy causes all this wild motion. The sliding, the chaotic bouncing, the extreme phase changes, it's all driven by heat. But what if we went the other way? If we could flawlessly extract every single drop of thermal energy from a substance, reaching what scientists call absolute zero, which is a staggering minus 273.15 degrees Celsius, what completely still, utterly frozen reality would exist? What actually happens when the chaotic dance of matter stops entirely? Think about that next time you watch an ice cube melt. Until next time, stay curious.